I want to set the stage for you that way so that you can understand why some of what we're doing may seem to you unusually complicated or organized. So first, what is this project? Well, in July of 2015, President Obama issued an executive order which established the National Strategic Computing Initiative. And one of the goals of that executive order and the NSCI is to accelerate delivery of capable exascale computing system measured as shown here, 50 times the speed of, say, the 20 petaflop systems on applications. So you might notice we're not talking about flops or instructions per second. It's performance on full applications that matter, and comparing them to what they can do now on the US's fastest systems. And in that executive order, Department of Energy was named as the lead agency, along with DOD and NSF in that endeavor. And then there are deployment agencies that you can read: NASA, FBI, strangely enough, NIH makes a lot of sense, Homeland Security, and NOAA. So main thing I want to get out at the very beginning is that this project is not about building a machine, although machines will be built, but it's about getting a lot of applications ready for exascale to do things we can't do now, system software to support them and to serve as the bridge between the applications and the hardware that is also changing over time. So the applications, of course, if they're going to do something new, they'll be different from the ones that are in use today. And then we will work with the vendor community on hardware technologies. So I emphasize it's the vendor community, so it's not academic exercises at this point in time, because we want the vendors to come up with products that can be implemented and be a part of a product line, not just a one-off special system for us. And we recognize that it takes people to do all these things. And so one of our essentially side activities, but an important one, is workforce development. So because it's a project, it's organized within the Department of Energy and explicitly between the Office of Science, which many of you might be familiar with. So one of the offices of the Office of Science is Advanced Scientific Computing Research. But then there's also the NNSA, which, as Thomas mentioned, had the ASCII project some years ago that I was involved in for a while. So the fact that it's those two parts of DOE also governs some of the way that we've organized things, because the National Nuclear Security Administration part, it does involve some classified applications. However, on the system software area, those are not classified, and so we're working with them openly that way. Projects have a beginning and an end, and so this is a 7-year project. It's led by the DOE laboratories, and what that's meant to indicate is that it's not led on a day-to-day basis by program managers in headquarters. We need to work with and are working with academia and industry, and we always talk about sustained performance as opposed to peak speeds. So our goals are to foster application development, because in the end, if you don't have applications that are ready to use the systems, then there's no point in building the systems. At the same time, the applications provide a lot of the requirements for what the system software should be as the applications evolve in their needs. They also guide some of the hardware developments. I think we'll have to do a lot of the software stack. Certainly the vendors provide some of the software, compilers and so on. But traditionally, a lot of the libraries for I/O, for mathematical subroutines have been developed at the national labs and at universities, and so we intend to continue that. I'll give examples of those momentarily. In what I label as a rich exascale ecosystem, we'll be working with vendors, funding them to do some of the research, to come up with systems that meet that performance goal, And we also see as part of our responsibility trying to create both hardware and software that will be of use to industry in order to help the economic competitiveness of the country. And so that one way to think of it is that we hope that the software stack that we will develop jointly with industry and academia will be such that it will be useful to industry as well. Not necessarily the end applications, but certainly the ecosystem that the applications depend on, and that the hardware will be such that it would make sense for a company that maybe isn't very big to buy a small version of a system that, when made into a bigger system, would be building blocks. So again, there would be an easier way for industry to take advantage of the technologies. So a lot of emphasis on that, because we want these to be real products, again, not a one-off system for us. Now, we use the phrase capable exascale system, which I believe occurs in that executive order. So we defined it by the speed metric, again, based on applications, a power envelope, and that's because if it took 600 megawatts, you could do it, but that wouldn't be very practical. Rough order of cost of a megawatt per year is $1 million. So a mere 20 to 30 megawatts is only an operating cost for the power of that, and that's for the system, not including necessarily the storage. It shouldn't break down too often, and so our goal is no more than once a week as perceived by a user. Now, in practice, pieces will be failing much more often than that, but the user view should be no more than once a week. And to my mind, it has to have a very good software stack that supports a lot of applications, not just a couple, to be worthy of being called capable exascale. So given that background, the way we've organized the project is in 4 activities that we call focus areas: application development, software technology, hardware technology, and exascale systems. Before I forget, I should point that exascale systems does not include buying any of the exascale machines. So this project will not buy the big machines. And that actually makes a lot of sense, because it's a project that will end in 2023. So who would be taking care of those machines? So instead, it's the facilities that always buy the big machines within the Department of Energy labs that will get it. There are Livermore, Los Alamos, Sandia, Argonne, Berkeley, and Oak Ridge. Now, those 6 labs are the ones that, every couple of years, one of them will get the leading edge system. So it will be those facilities that will issue the RFP to buy it, and they'll get it. And that's very important, because again, these need to be production systems, not just a research prototype, and they have a life of their own well beyond this project. So it's I think the right way to go. It does mean that we in the project are dependent on the budget for those facilities. They have to actually have the budget to buy the systems and at the right time. But we get a lot of benefits from it, because they can guide us to make sure we're doing research that will lead to the right kinds of facilities. So I'll give a little bit more description of all these areas in a moment. A quick summary is that it's a 7-year project. Co-design throughout is a very important part of the way we're approaching it, including integration. The first system we expect to be delivered in 2021, and then a second system in 2022. And typically it takes a year after delivery for systems to be in production as a accepted and fully production quality system. And as I mentioned, it's the facilities that will buy the systems. We talk about it being advanced architecture. Now that's a deliberately very vague way of describing things. So what's advanced? Well, something that will be a transition that will get the US on track to have capable exascale within a small number of years, as opposed to just an evolutionary path for projects, for commercial products, which we believe, if it were just evolutionary without any investment, we would not be anywhere near what we call exascale. It would use a lot of electricity, and it would not have the power to do 50 times the performance of today's 20 petaflop systems. So, in these matters, you have simplistic diagrams like this one. So this is just meant to say there's this one-time push, and now you're in a different trajectory. And so the trajectory will be elevated by advanced architecture. We do want to emphasize that we're not tied to any particular vendor or even type. It doesn't have to be GPU based. It doesn't have to be many core. We're open to any architecture, so to speak, that meets the needs, so long as, however, it is part of a product map for a company or companies. We hope to have several companies. And I mentioned there'd be 2 systems at least delivered, and they have to have different architectures because we don't want to be tied to one company and one type of architecture. So that will mean, improvements in the way parallelism is implemented and programmed. Memory and storage is always a huge issue. Reliability, as I mentioned, and energy consumption. So our timeline is shown here. So the first few years, you can think of it as we'll be doing research and development on the applications, on the software stack. The vendors will be doing research on the hardware technologies. And then after that, the following 3 years or so, there will be contracts signed to build the first systems. So at that point, the applications and the software developers will have a pretty good idea of what the machines will be like, and they can start changing their software and approach to be effective on those systems. The NRE that's shown towards the middle of the slide here, NRE System 1 and 2, that's non-recurring engineering, and those will be contracts given to vendors, and those are part of this project, to give more money to make the systems that would be bid even better, and to continue the R&D that was started under hardware technology, so that there's more people, resources available to improve the systems. And of course, we'll have test beds, which will be relatively small systems. Those the project will purchase, but site at a facility so that we don't have to set up a new facility for those. In the bottom, you see the facilities, the activities outside of ECP, which I've already alluded to prepare the site and to do the RFPs and the contracts for the systems, ending in 2023 sometime. Now, 2021 is, although it sounds like a long time from now, it's actually a pretty aggressive schedule for what we're trying to do. Now, it's not as aggressive as China has. They're aiming for 2020. We are not. But 2021 is still going to be quite a challenge. Now, because it's a project, we have a work breakdown structure. The reason I show this, although it's a bit of an eye chart, but I assume these slides can be made available to people later, is to indicate a couple of things. There are people's names associated with all of these activities. So at the bottom of each column, you'll see the first leftmost column, the word integration. And so Julia White is the manager of integration, because integrating all these activities, especially the software and the applications, is a big and very important task. And then at the bottom of the other 4 columns, you'll see co-design and integration. So Phil Colella is joining us, I think, basically this week to lead the co-design and integration for applications development. Applications development is the science and energy apps, the NNSA applications, other agency applications. The first one is one from NIH. And then we have a separate element for developer training and productivity. I'll say just a few more words about that later. And again, so co-design and integration, somebody has to be responsible for that. Rob Neely is for the software stack. You know, we are still working on some elements of it, but Jim Angus doing co-design integration for hardware, and Susan Coughlin for the systems. And those people have to be talking to each other all the time. So this is a lot of extra effort, but without it, we would end up, I'm afraid, with software that doesn't meet the needs of applications, and applications that might be actually spending more effort than they need to because they'd have to do so much of it themselves, of the implementation. Now, some applications have teams already that can do that pretty well, but many do not. So it's a big, fairly complicated project, and a lot of the challenges are, you know, this management of guiding the activities where everything is changing at the same time. The hardware is changing, the software stack will have to change and evolve, and the applications certainly are. To help manage this, or to help guide us in the right direction, I am establishing two advisory bodies. One is an industry council, and that's very close to being announced, and one is a science council. Now, the industry council is end user industry, so not the computer companies at all, but it also includes some vendors of software that's widely used by industry. So I can say in this audience, there will be a representative from Eli Lilly. So, you know, we have some pharmaceutical companies, automobile manufacturers, airplane manufacturers, jet engine manufacturers, and so on. And as you might expect, that's because we really do want to end up with a product that will be useful for those companies. And so they can help us guide that. And to be honest, we also hope that they will help us keep the money flowing from Washington, because if they are willing to say to Congress that this is important to them and it's not something that they could do on their own, then, you know, we have a little bit better probability of getting the funding. And then the Science Council is, you know, to make sure that we don't miss opportunities. You know, we try to know what's needed, but in my experience, every time I've had reviews from external experts, they pointed out something that could be improved. So I'm looking forward to setting that Science Council pretty soon. So what have we done so far? Well, we've been acting as a planning agency. We've done a lot of planning in the 15 months that this project has been underway. And over the last few months, we have funded a number of projects. 22 application projects, I'll show them in a moment, on the order of 35 software projects, and 4 co-design centers. And these are a different type of co-design activity than previous one, but I'll explain that. So the applications are, you know, 15 full funded applications, and then 7 seed efforts. The seed efforts get only $300,000 a year, and, you know, we hope to be able to grow them to more than that. So under national security, I just say stockpile stewardship, and you can fill in the blanks if you happen to know what would go on there normally. But then energy security, turbine wind plant efficiency. Driving down from Chicago yesterday, we went by maybe 1,000 wind turbines. It's an incredible number. Nuclear fission and fusion, reactor materials design, subsurface capture of carbon, high efficiency, low emission combustion engine and gas turbine design. You know, these are all projects that we bucket into energy security. Economic security, additive manufacturing, urban planning, that's a seed project. Reliable and efficient planning of the power grid. You know, anyone who's looked at the U.S. power grid can understand there are real challenges to inject, say, the wind turbine electricity, which is variable, and not end up with a lot of wasted energy and also faults. And then seismic hazards. Scientific discovery, as usual, we have, you know, cosmology, plasma accelerator design, and you know, lots of materials properties, ITER, and chemistry. Climate and environmental science is an investment as well. And the NIH related project, so it's funded jointly by NIH and DOE in this project, is for cancer research. So with the National Cancer Institute and National Institutes of Health. I hope that we'll have a couple more projects with other agencies, NASA, for example, but that's to be determined. So all these applications have to spend some of their time working with the software people. Now, let me turn to the co-design a moment. Application motifs, which were born with the name initially the Seven Dwarfs, from Phil Colella. Now they have the more genteel name, I guess, application motifs. I don't know if the ogres will end up having a different name eventually, but I like the ogre name myself. These are algorithmic methods that are used in a lot of applications, and so these are well known. This is not a product of this project. We're just taking that, and then we looked at proposals from about 50 application teams and tried to determine, okay, so what are they using? And so you can see the green rectangles. The cosmology certainly uses particle for methods for some of their simulations, sparse linear algebra, spectral methods, structure grids, and graph traversal, but not too much of the other stuff, and so on. So we went through all of that to try to decide what are areas in which having co-design centers that will help some of those methods, we would like to fund more, and perhaps we will, but we started out with these four. One is oriented towards data analysis. It's only one. I wish we had more. Ian Foster is leading that one. And then block structured AMR, John Bell. Then discretizations for PDEs and particle and cell methods. So each of those will be working with several of the applications I showed a few slides back, because they need this. And the hope is that, for example, for particle and cell methods, then we'll end up with implementations of methods and their implementations that can be used well by several of the applications, and therefore get both a better product and economies of effort. The training part of application development is certainly on the latest methods and so on, but also software engineering, because many people who develop scientific software don't use software engineering methodologies. And yet we think for the applications that are being developed to have a long and healthy life and be able to evolve, as they will have to, it would be good if they follow good software engineering practices. So we will help with that. And agile software development tools and methodologies. And this project is taking over the Argonne training program in extreme scale computing that I established a few years ago, because that's aimed at training people, especially for the first part. And we'll do some productivity analysis as well. For software technology, we have high dreams, and I hope many will be realized. So we'd like to build a comprehensive and coherent software stack that's useful for exascale applications of all kinds. And our approach is first extend current technologies where it's possible and makes sense. Do research for new approaches where the current technologies don't work. Coordinate with vendors because they provide part of the software, and end up with production quality software, not just demonstrations of new methods. So our conceptual stack is shown here, and we include the applications and co-design not at the very top, because we see them as using visualization, data analysis, and correctness methods but we have resilience going from top to bottom because we don't think it's something you can say it's one layer's responsibility. You have to worry about resilience throughout. And for workflows also, we consider them to be top to bottom. The other things you can see, this maybe in the past we wouldn't have software for memory and burst buffer, but now that we have additional layers of memory and then non-volatile memories that can serve as burst buffers, perhaps in each node, perhaps aggregated, there's software involved for that. Data management is always a big deal. And you'll see runtime both here and of course there's runtime down here. One of our hopes is that we can end up with fewer runtime systems to support the tools than is the case right now. And so we hope to have an influence in that. Now the requirements we got by looking at what the exascale applications proposal said. I'll show an example of that in a moment. Look at what's being used now at the DOE facilities. So things that are used heavily now, MPI is the obvious example. We think there needs to be an MPI, even if maybe a lot of applications in the future won't know that they're using it, but it has to be in there somewhere. Our guess is as to what's needed for exascale and what the vendors will provide. So here's one example from a nuclear reactor proposal. And we asked the applications to rank what they were planning to use by definitely plan to use, will explore as an option, or might be useful, but they don't have any concrete plans. And so for programming models and runtimes, that application team said, well, they would use C++, C, Fortran, MPI, OpenMP, Thrust, CUDA, and Python for sure, essentially. But they might well use COCOS, OpenACC, and they might look at Raja and Legion and HPX. And so the same thing for tools, for mathematical libraries, data management and workflows, data analytics and visualization. And so we ended up, if we looked at all the application proposals with all these pieces of software. So, how do we choose which ones we deal with? That's a pretty big number. And we want to try to pare things down if possible. But in some areas, we have decided to support several things that have the same functionality or goals, because it isn't clear which ones are the right ones. It's too early, we think, to make those decisions. And so there's a laundry list, so to speak. And so here's the software stack diagram populated by specific projects that recently we announced we would start funding evolution of. And again, I'll leave these slides. Some things are to be expected, right? Scale-Pack is going to be in there. MPitch, OpenMP, and so on. So those are things that are just now beginning to get underway. I think it was only October when we announced these. Okay, so that's what we're doing about software. I'll circle back to that a little bit. So for hardware, as I mentioned, we're funding vendors, and so we want them. So we issued an RFP in late June, I think. Got the results in July, and in August we selected some companies, a handful of companies is all I can say right now, to write a contract for maybe new node designs, new system designs, new memory designs, maybe new interconnects, silicon photonics kinds of things. And there are boundary conditions where we wanted results within 3 years, and we wanted to have confidence that these, if successful, would become part of a product that would be bid as a system, as part of a system in 2019, the year 2019. And so they had to specify what their plan was, who would be the company that would adopt it if they're successful. Of course, in some cases, it's within the company itself. So I am hopeful that later this month or probably mid-February, we can announce that, those contracts. And then we'll involve the applications teams and the software teams in quarterly meetings with these vendor teams to find out what they're able to accomplish, give feedback to them, and try to do co-design continually with them. It's a fair amount of money that we're devoting to this. This is a number that was published when we issued the RFP, so I can say it's about $300 million for these contracts. That's a fair amount of money. Now, mind you, some individual companies said they needed close to $1 billion to do things that would be useful to us. But we discounted that a little bit. But nobody's getting $300 million. That's the total for, I'll say, a handful of companies for 3 years. So it's a lot of money. Will it pay off? Well, we think it will, because we've done things like that at a little bit smaller scale, we being Department of Energy labs, and it has resulted in some useful advances. And frankly, we want to keep more US companies interested in the high end, because if we don't have a Cray and IBM, Intel, Silicon Graphics is now, of course, part of Hewlett-Packard. If we don't have those companies at the high end, then we'll have to rely on non-US vendors for the very high end. So, so the hardware technology part of the project is primarily in dollar amounts, these contracts, but there are also people involved to evaluate continually what comes out of these projects, and do abstract machine models to try to evaluate different possible architectures and some system software as well. So I think I probably said all this, the goals of this part of the project. So by doing Path Forward and then the NRE, the non-recurring engineering that I mentioned earlier, we hope to, and then co-design throughout, as it shows along the bottom. And the NRE application readiness, it's having real applications very early on the systems. We hope to end up with systems that are useful to the nation for a lot of applications, are affordable, not cheap, but at least affordable, and available in that time frame. Now, let me then get back to gaps and challenges. I've alluded to many of them going along, but to be more specific, these are the 5 objectives stated in that executive order. The first one, accelerating delivery of a capable exascale computing system. This is a verbatim quote. In that executive order, they use 100 times 10 instead of 50 times 20. So I think you can do the arithmetic. So that the exascale computing project is the project that's doing that, or attempting to do that, because DOE is the lead agency, and DOE has decided to do it via this project. Now, we are working with DOD, and you can probably imagine which parts of DOD that sometimes has done specialized hardware designs. So we do work with them to see if some of our needs are of interest to them, and perhaps they're funding something with hardware that would be of interest to us. So we are doing that as well. The second one, increasing coherence between the technology base used for modeling and simulation and the technology base for data analytic computing. Now, that's something that would be of keen interest here at Indiana University. And that's partly why I'm here today. In fact, because I hope to learn from the subsequent speakers things that I need to know. We're attempting to do some of this, but as I will indicate, we need to do more in this project. The post-Moore's Law era, that's outside the scope of this project. But I certainly hope that there will be good funding and good research programs in that, and they need to get started now. Perhaps that will happen. The Department of Energy Office of Advanced Scientific Computing Research a couple of months ago created a new division It's had the research division, the facilities division. Now there's a third one. It's called the advanced technologies division. Now this exascale computing project is part of this new division, but the other is meant to be post-Moore's law era, so quantum computing and so on. So I hope that there's a budget for that, not just the name of the division. So that's something that I believe needs to be done, but it's not part of this project. Increasing the capacity and capability of enduring national HPC ecosystem. Well, you know, we hope we're contributing some to that, but I see some of that as being more National Science Foundation, and I hope that, that those investments will eventually be made. And then the public-private collaboration, we are trying to do a little bit of that, as I mentioned, not just with the Industry Council. So I hope we can do some of that. But you know, there are a lot of things that need to be done we're not doing. So we're only partially tackling that convergence of simulation and data analytics. As I mentioned, the other is out of scope. So risks and challenges. For the applications part, you know, the applications have to face, you know, how to exploit this unknown memory and compute hierarchies. Programming models, you know, the question I frequently get is, you know, what programming model should I use? As well as what's the memory architecture going to be like? And I don't have good answers yet for that. So we're investing in several because we don't know which one. Integrating the software components, you know, that use different approaches, you know, with unknown parallelism of various kinds. You know, integrating the co-design motif-based community components. Presumably there's a good payoff in that, but it won't be easy to do. It may require rethinking some of the application code, and for some of these application codes are fairly mature, they need to evolve, but it isn't easy to plug and play right now. And portability of performance is one of the things that we will be measuring. And it can't just be done by a branch at the top saying, if GPU do this whole branch and if multi-core do this other branch. Multi-physics coupling is complex, and it's not just a software issue, it's also an algorithmic issue. Sensitivity analysis and especially understanding better the requirements of data analytic computing. You know, we need to have more applications that are actually doing that, because I really want to focus on real requirements from real applications to determine what we do. And even that's going to be difficult. So for software technologies, you know, the usual challenges are scalability, memory hierarchy use, power now, because moving data uses a lot of power, performance portability. But perhaps the biggest challenge is co-design and integration of the components of the software stack, so that they will actually work together, that the different runtimes work with different tools, instead of each tool having its own runtime, for example. And working closely with applications. So one way we're approaching this is that, because it's a project, there are milestones typically every quarter, and so some milestones will be shared by an application team and one or more software projects. And by shared, that means they're both responsible. They can't say, well, those guys didn't deliver what we wanted, or they didn't explain to us what they needed. So it's a contact sport. They have to work very closely together. So that's not a technical issue, but it's a very practical issue. You know, the dream is that it is possible to develop a software environment that relieves a reasonable amount of the work from the applications. You know, there'll be an initial additional effort, but over the long term, hopefully there'll be a payoff. And so one of the things we're going to do, because we know we don't have everything covered, is do a gap analysis, talking to vendors to see what they're planning to provide their software stack, and also talking to more applications, more types of applications that we don't necessarily have represented yet. And then budgets allowing, I hope we'll have budgets to do it, we'll do another RFI and RFP to the community, including the university community, not only the national lab community, for more software stack components. So I hope that we can do that. I think we need to do that. You know, right now we've been doing, as I mentioned, pretty much bottom up, seeing what's in use, what do applications say they need, and then selecting some of those projects. And that's important, but we also need to do some top down, I think. We need more applications that involve big data or large scale analytics, and certainly need more for workflows. We decided not to invest in workflows on the first wave of software projects, not because they're not important. We think they're extremely important, and in fact, will be more important over the next few years. But we didn't feel we knew enough to choose wisely. So I hope within this calendar year at the latest, we will invest in workflows, but based on more analysis and more investigation. Same thing with resilience. We're doing very modest investment in resilience, but doing a technology watch and then investing more heavily, I hope. So that's my analysis. I did leave some time for questions on purpose, although I know there's a panel session towards the end as well, but I really wanted to see if people had questions about any aspect of what I talked about. And again, I'm here partly to learn, because you know, we have this behemoth project and we have a lot of things underway, but there's still a lot to be done, a lot of things that have not yet been decided. So there's a real opportunity to influence what we do, and I welcome your advice and suggestions. Thank you.
Yeah, question.
Right.
Presidential directive and NSCI was premised on reestablishing U.S. leadership in this area in high-performance computing, feeling like we were falling behind, perhaps some of the things we see going on in other nations. I'm curious what you think now is going on in other nations and their progress relative to our progress on exascale, and are we on a path that puts us back at the top, or how do you see the international landscape for exascale?
Right. Well, certainly, I suspect strongly that the executive order was based on the understanding that perhaps, although we might still be in the lead, depending on how you measure the lead, it's precarious. So China has had a system in the top 500, whatever that means, for 3.5 years uninterrupted. It's been 2 different systems, but it's been Chinese systems. And the latest one, which was well after this executive order last June, is not just a little bit faster, right? Factor of 4 faster. I just read what is published about the Chinese plans, and in 2020 they expect to have an exascale system. I haven't seen a definition of exascale by them. Maybe they mean an exaflop, but I am confident that they will accomplish that on schedule. So that will happen in 2020, which is obviously before 2021. So in that sense, we would still be behind if you measure it by, say, top 500. But we're not measuring by top 500. We hope to be able to support a lot of applications. Now, of course, the Chinese systems are supporting applications now. So China is ahead by the top 500 measurements, and I think will continue to lead us in terms of what you call exascale. But my hope is that by, if not 2021, we'll be possibly ahead of them with that system, and then the next 1 or 2 systems will be well ahead. Japan has a project for exascale, and they're going to be a little bit longer as far as I know. They had 2020 as a goal, but recently announced it'd be delayed a couple of years. I don't think it'll be a couple of years myself, maybe only 1 year. But Japan is a contender, absolutely. They have a very good track record as well. And then the European Union has allocated quite a bit of money that they haven't yet distributed, but that's aimed at exascale. Now they have less of a track record for these kinds of things, but a lot of money. So I would say that if the United States wants to be a leader in HPC or near the top, that some investment such as this project needs to be done. Will the next administration that's about to take office want to do that? That I don't know. But it certainly is the case. It's an international competition. And the economic aspects of it, I think, are fairly clear, that it does matter. And it's not by selling a bunch of computers, but what you can do with the computers. Thank you. Yes?
You talked a fair bit about applications, and I think the very kind word that you used was some of them are rather mature. And so I wondered if you think about things that are long-standing, like high energy physics application for, I'm sure, NNSA, the nuclear programs. How do you adapt those in the ways that you described while also sort of maintaining that mature code and not having a giant tower on your head?
Well, yeah, that's an excellent question. It's been a problem for a long time. Well, the investment in dollars that we're making to those application teams are so that they can have more people involved, because after all, it does take people. Some of those mature applications, mature doesn't mean stagnant, right? And some of them are designed rather well so that they can be evolved. But it is the case that typically an application team has funding to deliver scientific results. And so if they have to simultaneously deliver scientific results and do major adaptations, they don't have enough people. So that's what we hope to be doing. That is providing enough funding to hire, another 10 people perhaps, in some cases to a team, but have them be part of an integrated team. So, one of the several conservative decisions that we made was to invest mostly on existing applications that have a track record and that have a very good team in place that's survived some evolution across different kinds of architectures and different kinds of parallelism, and invest in those teams as opposed to investing in something completely new. So the people involved are the key, but they do need more people. And so that's one of the things that I like about this project, because in the past, when occasionally I've been involved in putting in place a very big new computer, applications colleagues have come to me and said, okay, Paul, so we got a bigger computer, but I don't have any more people, I don't have any more time. How can I make use of it if it isn't exactly the same architecture that they're already using, which these days tends not to be the case. So we hope that mitigates it. And then, for the teams that don't have as good software engineering practices or design of the software as others, that's where we're hoping to supplement that with, the training programs, as well as, again, being able to hire people that have that expertise and become part of the team. Yeah, applications are in this project really the key thing. At present, it's the biggest single part of the budget is going towards that collection of application activities, which is different from sometimes in the past where there's more on the hardware. Thank you. Question?
Yes, sir. An online viewer asked, the ECP recently announced a 2021 exascale deployment based on a novel architecture. What is meant by novel in this case? And what role do you foresee system software playing in conjunction with this novel architecture?
Thank you for the question. We decided, in fact, to change the phrase from novel architecture to advanced architecture. So in these slides, you saw advanced architecture because even though that's difficult to define as well, novel just seemed inappropriate. So what we mean is that we're open to systems whose building blocks are different from building blocks that exist right now in the top systems. So one practical way to define it would say if you look at the top 500 systems, architectures, there are some potential architectures, none of which are implemented in the top 500. But yet, we would welcome and evaluate very seriously a new building block that doesn't exist now in any big system, but could credibly be used to build an exascale system by 2021. You know, it could be a different instruction set architecture than the ones that are mostly there. You know, the ISA for about 90% of the top 500 is the Intel x86 architecture. And there's Power 8. Maybe there's a different ISA that isn't represented. That would be an advanced architecture. Another would be perhaps using FPGAs for part of the system. So what we're trying to signal by using this vague term, advanced architecture now, no longer novel architecture, we want to signal that we really are open to new ideas from vendors. We want it to be part of a product roadmap, not just a research activity for proof of principle, but we definitely will consider very seriously a new type of system architecture or building blocks that are different. Did I miss part of the question? I know. Did I cover that? Yes.
Paul, as for the timeline from 2021, is it expected that the year before the timeline, the architecture is being laid out and the system can be developed, or is the 2021 the timeline that you think I have now the architecture defined, and now beyond the 2021 actually deploy and build such a system?
Thank you for that clarification. So I'll have to be more clear in future talk. The 2021, it would be the delivery of a full system. The timeline for signing a contract for that system would probably be the year 2019. It could even be late 2018. So at the time of signing the contract to build a system, we will know a lot. Now, I didn't say we will know everything, because typically, since these will be first-of-a-kind systems by definition, the vendor will say in good faith that this will be the hardware design and this will be the software and how it will behave. In my experience, typically when it's delivered, it will, or when it's almost time to deliver it, some things won't work quite as expected. Because, vendors will say, this part of the hardware we ended up not being able to implement efficiently or at all. But we will know a lot, either in late 2018 or 2019. And then as the system is being built, there's time to do something about the software and the applications. So that's the plan. So in 2021, the system would be delivered. It would be tested and accepted over a period of 6 to 12 months, typically. The applications would have some access to the system during that initial period, because they would be one of the tests to see how does the system really behave. And then in this example, in 2022, it would become part of a production facility and managed the way the systems are today at Argonne, Oak Ridge, Berkeley, and so on. Does that answer your question? Yeah, so it's very important that we have this time lag. You think, well, you sign a contract, then you have to wait 3 years, 4 years for the system to arrive. Yes, that's the way it works in this environment.
Paul, I had a question.
Yes, Jeffrey.
So obviously you have a lot of DOE people working on this. How best can people outside DOE do things that could help this project? Like look at nifty new hardware which looks like your hardware or something like that. And is there anything DOE you're doing to try to make contributions more useful?
So I hope that we can do something. One small thing is I hope that we will be able to issue a request for proposals that's explicitly aimed at university community for the software in particular, because a lot of the expertise is at the universities. Now, through the parts that we have funded so far, there are on the order of 15 universities involved, but not as the lead of the project, but rather a contributor to a project. So these are typically, longtime colleagues of yeah, the Jack Dongara would be the poster child, right? Yeah.
Actually, I wasn't really trying to raise money, but I was just thinking, let's take a discussion we're having here. I said we really ought to have some Intel mini-core systems on campus so that we can actually explore both the architectures DOE has. So, so I'm thinking that there might be some principles you can negotiate that would allow work outside DOE help this national activity. Given this is meant to be a national strategic initiative.
Right. Yeah.
So you can then harness, it's like the Apache Foundation contributing free, so we could do what we would normally do, but do it in a context that was more helpful to you.
Well, certainly, we should be able to provide access, we DOE, to the latest systems anywhere. So Argonne now has in production a system called Theta, which is only a 10 petaflop system, but it does have the Knights Landing type of mini-core. And so I would hope that would become available, under the usual, proposal process to you or, people in this room. Because you're right, some of it does depend on having access to the hardware and the software environment. There are a lot of things that we could benefit from with that, because you could demonstrate something very specific in that case. Yes.
And then in addition to having access for research, you might also have access for students. Several of us are teaching some of these massively open online courses. And so by providing some of the more advanced students with access to these architectures, I think we would learn better about how to teach larger numbers of that could be useful.
So you're suggesting the students are something that the universities can contribute?
I think just teaching materials in general. I think you will need to empower many different scientists, but also many different industry representatives and government representatives. So for also to use these new shiny systems. And so you will need quite a number of courses to do that well. And I think that's what many of us trained for. Develop new ways of teaching in these online environments that are effective.
True. I would say perhaps what I would prefer is that you encourage your students who are interested in this type of research to come to the labs for summer appointments, dissertation support appointments, which can be not just in the summer, but any time of the year. Many people who are now at the national laboratories or back in academia have spent time at the national labs and have really contributed huge amounts. So that for this project would be a quicker payoff, and it would have, I think, lasting benefits for the nation. Because having experience at the national labs, it doesn't mean you have to spend your career there, but it really can help accomplish things and get an idea of what the problems are that people care about. The training program that we have is a 2-week training program in August typically. We usually accept 60 to 65 participants. About 3/4 of them, or maybe 2/3, are advanced graduate students from universities, and the evidence seems to be that it really helped them. Some have, the next year been able to get a paper accepted at supercomputing, for example, where, I know some full professors whose papers have not been accepted at supercomputing. More human contact is what I would prefer. But you're right that the coursework also could benefit us. And we should at the very least make our many participants in the project aware of relevant coursework that's available online or streaming. I will take note of that. Any other questions?
Well, maybe I'm allowed another question.
Yeah.
So you have a nice set of slides which map applications to teams and software.
Right.
I may be wrong, but my impression is that there's not any terribly many authoritative review articles or lessons from, say, your DOE's research and also actually NSF research. Somehow we're not capturing these in a very clear fashion. Maybe I'm wrong. That's my impression. So that might be that you could have a more robust plan if you somehow we got more of these more thorough surveys of existing.
That would be very valuable to do. I agree with you. I don't think we've done that very much in the national labs, and my hope would be that, say, a year from now, order of magnitude, you know, we would be able to have people write such an article that would be useful. Yeah, I certainly like that idea very much.
In fact, in the area you mentioned, data analytics, one of the troubles I have in data analytics, it's extremely difficult to discover what scientific fields want to use or might use in the area of data analytics. Is astronomy going to use clustering, deep learning, ...
Right.
It's not obvious at all, as far as I can see. That makes it relatively hard, actually, to make strong statements, in my opinion, about what machines might be useful and what software might be useful. That's another area where I think the community is missing a lot of potentially useful requirements analysis, but I don't see a good requirements analysis.
I agree with you. You've probably seen the Sandia report by Bob Leland and Bruce Hendrickson and so on large-scale data analytics, and you know, there's some fairly vague statements about, well, you know, large-scale simulation, large-scale data analytics have these differences or similarities, but they're at such a high level that I'm not sure that they're useful. You know, I mean, it's true that nowadays, even large-scale simulations, the floating point instructions tend to be only, say, 10% of the instructions executed. So why do we worry about floating point as much as we do? And you know, because of indexing and so on. But that's not enough to be useful. And yeah, so that paper attempts to do a little bit of what you said, but very little. Okay, Steve?
So where would you see that sort of information coming out? Whenever I talk to people at computing centers, they seem to think that application scientists don't really know the bottlenecks in their code for the most part. And I guess in my community, we think we do.
Yeah.
And so maybe it's these code design teams that would have to provide that kind of expertise from different areas that would get together and really study the problem.
Right. So the co-design teams are part of it, and also and I brought this up because I gave a short shrift. We're trying to put in place an effort for to also do a cross analysis of the applications with, you know, a small number of independent people to help assess, you know, the performance, what the bottlenecks are, what are the, you know, the real features of the application codes, and you know, we think that needs to be done independently. But what I'm advocating is in a collegial way. It's not a matter of, you know, you're getting an A- or something like that. But let's work together to figure out what's going on. Did you are you familiar with the Joule metric, Joule metric that was used a little bit by some of the DOE labs? So it was a project that no longer exists, but it was meant to try to get a feel for how some of the heavily used applications were using the systems, how effectively, and you know, what were the bottlenecks. And so you might think of it as a restart of that a little bit. And then there's the, so that I hope we get started later this month. And one thing that we're also about to start is, if you've heard of the IDEAS project that Mike Haru, Louis McInnes had, that's funding is ending, but we're putting together a similar project, and that's aimed at productivity as well. Yeah, so you know, we'll have to work together, you know, with people like Phil Colella involved, and Andrew Siegel, and Anshu Dubey, and others. You know, we hope we can do some of that. And then at that point, we could start putting out reports and maybe journal articles as well. I would like to do that. Okay, well, I'm afraid I've eaten into Thomas's time, so let me, I should probably
Thomas
close.
is not till 2:30. Okay.
Oh, did I have the schedule wrong? Oh, okay, very good. Excellent. Steve?
So will we have an API for energy usage in our codes? Is that important?
Well, I hope so. Right, because you want to be able to measure it. It'd be good if there were an API, although you know, different hardware will probably have different things that are measured. But we hope to evolve to that, and we do talk to vendors a little bit about that, because it's clearly important. And yeah, that's something that hasn't been measured much in the past, but over the last several years, people have started to do measurements.
And as you say, we usually design plots per second, and maybe that's not the right metric for assessing the efficiency of our code.
Right. Yeah. Yeah. So, in fact, Sandia has done a little bit of work that's certainly not just aimed at the flops, but it's just the beginning. But that's beside the point. If we don't have a nice API, it'll be much more difficult to both get the numbers and to then compare them, because you know, be comparing different things. Yeah, it's a struggle to get things. So a lot of the performance measurements, not just of power, but of other things, over the years, more and more has been available, and the vendors have been releasing, as I'm sure you know, more of the interfaces, because for a while they were there, but you couldn't actually access them unless you had a close friend in the company. And so I'm hoping we can do the same thing in power. Yes, that is one of our goals.
All right, so probably we should thank Paul again.
Okay.